Hey everyone. Our next lesson in Unit 8 is going to be on electric current. And this particular lesson, I think it's appropriate to use a river and flowing water to use as an analogy to electric current and voltage. And we'll tie resistance into that as well. But I want you guys to keep this idea of a river and flowing water and how exactly water does flow in a river. I'm going to give you two different scenarios here, and we'll see how you connect this throughout our lesson. Water has to flow. Of course, I'm not going to be able to do this straight. Water has to flow from a higher point down to a lower point, right? And depending on the steepness of this curve, water is going to flow faster or slower. So if we have a really shallow portion here, water is going to flow slower than when it's very steep here. Maybe this is like a waterfall or something. But the water flowing down the waterfall is going to be flowing a lot faster than it is over the shallow part. And if at some point here, if you think about why, I'll just kind of make this a barrier here. Why beavers build dams? What's the purpose of that? Well, if you think about the flow of water before a dam and the flow of water after a dam, water is always flowing slower here after the dam. So we'll see what part of how current ties into the dam here, the steepness of the slope, how much water is coming down any of these portions. How does the steepness or things like a dam affect how much water or current here is flowing in this river? So to start, we've got to have an understanding of what electric current is. An electric current is the rate at which charge passes a given point in a circuit. So how much charge every second is passing a particular point as charge is running through a circuit. Now a circuit is a closed path along which charged particles are able to move. So the circuit is almost kind of like the river. It's a path along which water is able to move or able to flow. And current, just like current in a river, is the rate at which we could take charge out of there and call that water. Current's the rate at which water passes a given point in a river. The higher the current, we always hear that high currents or heavy currents, you can get pulled under and dragged along the river because there's a lot of fast flowing water at that point. And the same idea is going to apply to electric current. Kind of the same idea. Now a switch is a device that we can use for making, breaking, or changing connections in an electric circuit. Kind of like if you had a railroad track here and you got to I'm probably not going to be able to draw this very well. Surprise, surprise. A switch that's going to allow you to go left or right. The switch is right there in the middle. It's going to allow us to make, break, or change connections in a circuit. It doesn't quite look like that. It looks a little bit different. And we're going to be doing some practice doing our schematic symbols because you do need to know how to draw these. It's going to look something like that. And you'll see some variations. Sometimes there's a little notch here or a notch here that just kind of shows that's a point that can pivot or a point of contact there. But the way that this is written in your reference table is just simply, and I'll try and draw this a little bit more clearly, is simply that. That's our symbol for a switch. But you'll see it in a variety of different ways. But basically, The arm here can open and close to make or break or change a connection in the circuit. In this case, it opens and closes or makes or breaks that connection, but it could also switch to a different spot. Maybe there's a connection up here that's switching between two parts of a circuit. The options are quite literally endless. Now, our SI unit of electric current is what we call the ampere. We more commonly refer to that as an amp, represented by the symbol capital A. And we can find current given the equation delta Q over T, which really is the rate at which charge is passing a given point over time. Now I, our current, is measured in amperes. And that's represented by a capital A. Q we know is charge, that's coulombs, represented with a capital C. And T in time in seconds, represented by a lowercase s. Now, an ammeter is a device that is used to measure current. And this is given to you in the reference table. Just kind of like that, a circle with an A in the middle with two little prongs coming off of the end. Now we can take something like this, a device to measure current, and put it into a circuit to measure how much current is flowing through a particular point. We could also take this and put it into a river to measure how much current is flowing through a particular point at a particular time. So we put these, and these have to be used, and we'll learn more about this later, in series in a circuit, or basically it has to be in the path that the current's flowing. We'd have to put this thing directly into the river in order to actually measure the current. We can't just hold it on the outside and stick some prongs in there and measure the current. We'd have to actually immerse it into the river to measure how much charge or how much current is flowing past that point at that time. We'll talk more about series and parallel circuits later. Now we do need certain conditions in order to have an electric current. Now, in addition to having a complete circuit or a closed path along which our current can travel, one of the necessary items is a difference in potential between 2 points in the circuit. And that must exist in order for there to be an electric current. I'll liken this to your river. If the river is completely flat, so there is no change in height, from, let's say, A to B, we have zero change in potential energy. And if this is completely flat, water is not going to flow anywhere. It's not going to flow from A to B. It's going to sit there, kind of like it would in a puddle. So we're going to have no flow. So we have to have some type of difference in potential. This has to be greater than zero. A's got to be higher than B, or B's got to be higher than A in order to have some type of current. Now in a circuit, the potential difference is often supplied by what we call a cell, or it can be supplied by a battery. And these are very similar to each other. A cell is a device that converts chemical energy or chemical potential into electrical energy or kinetic energy. So we're converting here potential energy to kinetic energy in a cell. And we made these in chemistry, and we called them electrochemical cells. You guys did a lab on this. Now, a battery is a combination of two or more electrochemical cells. So if we take two or more, put them in combination with each other, we get a battery. And the potential difference can be measured in a circuit using a voltmeter. How original. Ammeter and a voltmeter. Easy to remember though. So the symbols that we have for a cell, and each of these have prongs coming off of them, and that's just so we can insert them into the circuit. This is our schematic symbol for a cell. And a battery is going to look like the same thing, but we're going to have multiple cells. In this case, we have two cells. You can see you got two portions there of a cell, which would make a battery. And we could continue on with this. We could do something like this. And we could essentially make those as big as we wanted. A voltmeter is going to look just like an ammeter, where we have the circle representing the meter with the V inside for voltmeter, and the prongs to show where we would insert that into the circuit if we wanted to measure the potential difference of that circuit. Now, positive charges, we know, tend to move from positive potential to negative potential, or points from higher potential to lower potential. We said those from positive potential to negative potential. Now, this is what we call conventional current. Current flowing from positive potential to negative potential. However, that is not necessarily the case. Negative charges can move in the opposite direction, or from negative potential to positive potential. And that is the treatment that we will use in this course. How negatively charged electrons are moving from a negative potential to a positive potential. This is what we call electron flow theory, as opposed to conventional theory. And this is the one that we will focus on in this course. Electron flow theory, how electrons flow from negative potential to positive potential. But both can be used. Just kind of depends on the application and the situation. Conductivity in solids. So conductivity is actually a specific property of a material. We know not everything can conduct electricity. And it's going to depend on the availability of charges, more specifically electrons, that are relatively free to move under the influence of an electric field. So if a material has many available charges to move when an electric field is applied, then they're considered or have the property of conductivity. And that property can vary depending on the availability of those charges. Now, metals we know are good conductors because they have a lot of electrons that are not bound at all or are very loosely bound. Remember, they are bound by metallic bonds, which allow electrons to be freely shared. So that makes metals good conductors. They're very readily going to give up their electrons. Now, non-metallic elements or compounds have electrons that are really tightly bound to the atom and have very few that are free to move around. And since they don't have a large availability of electrons, we call these materials insulators. They insulate the flow of electric current. Now, the lesson we're going to talk about today is resistance and how that connects to Ohm's law. Now, we represent electrical resistance with a capital R, and it is the opposition that a device or conductor offers to the flow of electric current. Now, this is where it's probably popping into your head now, I'm sure, where the dam comes in. The dam we're going to use to represent our resistance in the circuit or in the river. Now, Ohm's law says that the resistance of the conductor is the ratio of potential difference applied to the ends of the resistor and the current that flows through it. And Ohm's law, given to us in the reference table, is potential difference over our current, V over I. So we measure potential difference in volts, or capital V. I is current, measured in amperes, or capital A. And R is resistance that we measure in what we call an ohm. And we use, let's forget the name of that symbol there. I'll have to get back to you on that one. I'm drawing a blank on the name of that symbol. That's what it's represented with. And these are the same. I know mine looks very similar to that. And that's how we're going to measure resistance. Now, the ohm itself is equal to 1 volt per ampere. Volts over amps. And that's what Ohm's law tells us. Now, before we do our example here, I'm going to use a little simulator to kind of connect this idea of voltage, current, resistance to Ohm's law. So right now we have a circuit. This is a closed path. We have a potential difference here. This is a part of a, cell right now. And we can kind of think of this as a closed river that water is flowing through. Okay. Here's our conductor itself, our potential difference applied. And there's going to be some type of flow of current or charge flowing through this circuit. Right now there's 10 milliamps worth of current flowing through here. Now, if I wanted to increase our voltage, increase the potential difference from point A to point B in this circuit, or I wanted to make the slope of our river greater, increase the potential drop, maybe we want to see a waterfall, we're going to take the pitch of our river and make it steeper, 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 steeper until we get it to where it's completely vertical and we have a waterfall. What do you think would happen to the current or the flow of water in that river if we made the slope of the river steeper, all the way to the point of a waterfall? Well, let's see. Again, currents are water flow. We make the river steeper, 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 steeper. Our current continues to flow and gets extremely great. So the amount of water pouring over that waterfall is going to be a lot more than a portion of the river that is very shallow. So the steeper we make that drop of the river, the more water is flowing through it. We increase the voltage, we increase our current, our resistance is remaining the same. Now let's consider this a very shallow river. We have a low voltage, a low change in potential, low current. You're kind of standing next to a little creek and you just see a little bit of flow through that portion of the creek. Now let's say you started throwing rocks in the creek, or you saw beaver starting to build a dam, and you're starting to throw stuff into that creek or river that's starting to fill up and make a mound in it. You're adding resistance to the flow of that current. What would you expect to the current to do if we started throwing stuff in there? Would the current move faster? Would it move slower? When the beaver builds the dam, is the current moving greater or slower after the dam is built? Let's see. We increase resistance. Dams being built, rocks being thrown in the creek, greater resistance in the circuit, greater resistance in the creek. Current drops way down. We would now have very little flow in our creek. We have very little flow here in our circuit. So by building a dam in the river, it's decreasing the amount of current that can flow through that river, or the amount of electric current that can flow in our circuit. If we wanted more current to flow through here, whether that's water or charge, we could change the potential, which is going to give us more flow here. Current went up relatively significantly. So this is kind of like a dam being built on a very steep portion of a river. You're going to have a change in potential. There's going to be a lot of force here behind the dam. And we're going to have current flowing through it because there's such a great push behind it. We still don't have a whole lot of water flowing through it. The water coming through the dam is still going to be less than if the dam wasn't there. If we start to remove the dam or make the dam smaller, more current's going to be able to flow through that point. And let's try an example here. Students measuring a current of 0.2 amps flowing through a lamp connected by short wires to a 25 volt source. What is the resistance of the lamp? So we're looking for a resistance of a lamp. We're given a value of 0.2 amps flowing through the lamp. And we have a 25 volt potential difference. So let's define these specifically. We have an amperage of 0.20 amps. We have a voltage of 25.0 volts. And our resistance, we don't know how many ohms that is. Well, Ohm's law tells us that resistance equals the ratio of current, or excuse me, of potential difference over current. Our potential difference of 25 volts versus or against our current of 0.20 amps gives us a resistance of 125 volts per amp, or 125 ohms. Make sure we keep that in there. If you guys have any questions, make sure you write them down and make sure you ask them. For today, I'll leave you with a joke. What do clouds do when they become rich? They make it rain. Have a great day, everyone.